Hi, I'm Kaitlynn, environmental educator for Kentucky State University Environmental Education and Research Center, and today I'm going to be taking us through an activity called Ocean Osteoporosis. Joining me today is my coworker Ian Ries. He's also an environmental educator for the EERC. So before we get into the activity itself, I want to talk a little bit about what ocean osteoporosis is. I mean, that's kind of a big word. But for us to understand what ocean osteoporosis is, we also need to understand what ocean acidification is. And that's basically exactly what it sounds like. It's making the ocean become more acidic. So what is happening and what we have seen is that the pH of the ocean is going to start lowering, which is going to increase the acidity. And I know that sounds a little counterintuitive, but we're also going to take a look at the pH scale, and hopefully that'll help us make it a little bit more sense. So if we look at this pH scale, the ones written in red, that is our most acidic, where you're going to have the most hydrogen ions. Up in purple is our most basic, where you're going to have most of your hydroxide ions. So our drinking water, for reference, is around 6.5 to 8.5. It's a little off scale there, but that's all right. It's usually around 7 though. And what we've noticed is that our ocean's acidity levels right around before the Industrial Revolution was right around 8.2. So it's a little bit basic. And then directly after the Industrial Revolution, we've noticed a little bit of a decline in the pH of the ocean. So it is now sitting at 8.1. And that doesn't seem like a whole lot. It seems like a pretty minor change. But when we're talking about the scale of the ocean, every 1 pH unit that is dropped is equal to the acidity increasing tenfold. So what we've seen from dropping 8.2 to 8.1 is we are now at a 25% more acidic in the ocean than we were before the Industrial Revolution. So what causes that? A lot of times the major factor for ocean acidification is the increase in CO2 emissions. So basically what's happening is we're releasing all of this carbon dioxide into the air. It's being absorbed into the ocean by chemical reactions we're not really going to get a whole lot into today. But these chemical reactions are going to end up increasing the acidity of the ocean. And a reason why this is such a huge problem is because it is going to start affecting marine life. And the biggest hit that marine life is going to take is our calcareous organisms. So what's a calcareous organism? Basically, that is an organism that relies on calcium deposits in order to create a hardened shell. So we're going to be looking at coral reefs, we're going to be looking at crabs, we're going to be looking at a lot of our mussels. So when there is not enough calcium in the ocean for them to build up these hard shells, the acidity of the ocean and any kind of predation, any kind of disturbance, if they get knocked against a rock, it's not going to protect them as much as it normally would. And even in severe cases, in high acidity situations, these shells will even completely dissolve and break down. So we're seeing a decline in a lot of these organisms because of the rising acidity of the ocean. So with that said, we're going to go ahead and get into the activity, and we're going to do a quick little demonstration to kind of show how this acidity affects these animals. So what we have right now are these eggs over here, and these are going to represent our calcareous organisms. And we're basically going to build shells to protect these organisms from stressors in their environment. And to do that, I've got these nifty little ions here. You can kind of see them on the screen for a little bit. We've got our hydrogen ion, a calcium ion, and a carbonate ion. So what normally happens is our carbonate ion will bond with our calcium ion to create calcium carbonate. Sounds pretty fun. But that is basically what creates these shells for these organisms. So when we increase the level of hydrogen that is available for bonding in the ocean, because of certain chemical processes that, again, we're not really going to get a whole lot into, the chemistry gets a little complicated, but that hydrogen ion is more likely to bind with our carbonate ion to create carbonic acid. And because it is going to bind more readily with that carbonate, our carbonate is not going to form calcium carbonate as quickly. So for our first example, I'm going to scoot these eggs back out of the way. I'm going to present Ian with a bunch of carbonate ions. So I'm going to give you about 9 of these guys.
All right.
And this is going to represent a normal situation with the ocean. So I'm also going to give you 8 of these guys. One, two, three, 4, 5, 6, 7, and 8. And I'm going to give you a hydrogen. So let's say this is our ocean at our normal 8.2. So now we're going to start bonding all of these carbonate ions with your calcium ions to create your calcium carbonate. And you're going to count up how many pairs you have.
There's 1, 2, 3, 4, 5, 6, 7, 8 with an extra.
You do have an extra, and so you're going to have that bind with that. And because that happened, we have 1 less calcium ion that is just kind of floating around the ocean out there. So this will not go towards building any of our shell to protect ourselves with. So right now you've got, how many pairs is that? 1, 2, 3, 4, 5, 6, 7, and 8. 8. So you've got 8 calcium carbonate compounds that you have created over there. And so that is going to get you a whole box to protect your egg.
Nice.
So while you're putting your egg in your box, I'm going to run through another example with these. Can you pass me the rest of those there, please?
Sure thing.
Thank you very much. And so now we're going to look at a little bit of a different example. So we're going to look at the ocean post-industrial revolution. And so what that means is I'm going to have the same number of our carbonate ions. And I'm also going to have some calcium. But in this instance, I'm not going to have as many because I'm going to have more hydrogen. So let's say Ian had 1, let's say I have 6 hydrogen. Because this hydrogen ion is going to form a bond more readily with our carbonate ion, I'm going to have to bind those first. So that leaves me with 4 that I can use to build my shell. Remember, Ian was able to build 8. So now we're going to do that. So my shell is going to be significantly weaker, which means I can have this sad little strip of tape, and I can have this newspaper, and that is what I can have to protect my egg. So with that, we're going to go ahead and set up our egg drop real quick, and we'll see how this turns out. All right, so we've set up our little egg scenarios. Ian's got his egg in this nice, safe little box. I have mine. I'm going to wrap this piece of tape around there in the hopes that maybe it'll hold the shell together. I'm going to nestle it in this newspaper. And that will be what I use.
I think I have a feeling I know whose egg is more likely to survive this.
The higher acidity egg is not going to be faring too well, I think.
Yep, I think you're right.
All right, so let's go ahead and do the egg drop for yours.
All right. So I'm just going to take this book. We're going to drop and see how my egg does. We even fell off the table.
You've fallen down a trench.
I have. I've fallen down a trench. So let's see how my egg formed. And we're still intact. My organism lived.
All right. So with my sad little piece of tape here and my little nest of paper, you know what? We're going to turn it upside down and see if that helps at all. There we go.
All right, we're going to drop from the same height and see what happens.
It's looking a little flat.
A little bit.
And our egg did not survive. So basically what we've found with this is that we do need this calcium carbonate to build up a very strong shell to protect our calcareous organisms. And to do that, we need our ocean acidity to stay at the level that it is at. And with increasing ocean acidification, we are creating this ocean osteoporosis, which is just meaning that we are having weaker bone structures and weaker anatomical structures to protect our organisms. So with that, I hope you have learned something fun about ocean osteoporosis. I hope you can take away some of these chemical reactions with you. Give a big old thanks to Ian for helping us out with this activity.